All right, guys, and I also wanted to provide some information about getting through the AP problem that was in the same purple notes packet. So this one talks about having water in a conical storage tank, which just means we've got a cone filled up with some water. What it tells us is the height of the water in the storage tank is modeled by a differentiable function h, which is the height. So where h of t is measured in meters and t is measured in hours. So we're going to be looking at meters over time. At time 0, the height of the water is 25 meters. And then it gives us the rate at which the height is changing over a specified domain, so 0 to 24 hours, so 1 day. So what we want to take a look at here, as we kind of have evaluated and completed the majority of the derivatives work we're doing throughout AP Calculus, is to see what are the different types of questions that can be posed based off of the knowledge that we have. And what kinds of problems are we going to have to take one step further in the future to be able to answer? Because the more we can critically assess problems that way, the more prepared we'll be to tackle things at the end of the year when we know everything that there is to know for this course. So the first question asks us, when the height of the water in the tank is h meters, the volume is 1/3 pi h cubed. Then it asks, at what rate is the volume of water changing at time 0? So you guys, this problem is saying height and volume are related. We know the derivative of height, so what's the derivative of volume at a specific time? So as soon as you see two related quantities, you know how one changes over time, you want to immediately think, okay, I know this is a related rates problem. So this is not an optimization problem yet. Part A is related rates, and that's something we know how to do. So what you want to do for your related rates problem is to start with whatever equation relates the two quantities. So the 1/3 pi h cubed. So then we can take this equation and we want to go ahead and find the related rates components. So we've got dv dt is equal to, and then that 3 is going to come in front, so I just have pi h squared, and then I don't want to forget the dh dt. Now our goal is to solve for dv dt because it says what's the rate that the volume is changing at, and we need something to substitute in here for the dh dt. The problem gives us dh dt. So remember, dh dt is the same thing as h prime of t. So we have that equation. So we can really think of dv dt being equal to pi h squared times that whole thing, 2 minus 24e to the negative 0.025 t over t plus 4. Now that looks a little bit intimidating as an equation to get started, but the good news is we're interested in time 0. So time 0, which it tells us in the problem when the height is 25 meters. So we can go ahead and substitute things into our problem. So dv dt is going to be pi h squared is going to be pi times h is 25, so 25 squared. And then if I take a look at the structure of this equation, when time is 0, e to the 0th power is going to go to 1. And then down on the bottom here, 0 plus 4, that's going to go to 4. So I end up with 2 minus, this whole piece becomes 24, this becomes 4. So I'll end up with 2 minus 24 over 4, which is the same thing as 2 minus 6, which is going to give me negative 4. So if I just want to punch that into my calculator to see 25 squared, so 25 times 25, times negative 4, I'm going to end up with dv dt being equal to negative 2,500 pi units. And I could multiply that out too if I wanted to do a 3 decimal approximation, but it's okay to keep the pi there. And then my units here, since height was in meters, then volume is going to be in meters cubed. The time unit will be the same, so we'll have meters cubed per hour. So that's your part A. And that's a good exercise in related rates because not the material that we do on Monday, but on Tuesday, that content is going to be super related to related rates. So it's a good idea to go back and see that problem. And also, I want you to see the way that different applications for derivatives are put together in one free response question on the AP exam. Then B says, what's the minimum height of the water during the time period 0 to 24 hours. So remember, you guys, minimums are going to occur when your derivative is equal to 0. We are given the derivative in this problem. So let's kind of come on down this way for that part of the problem. We have h prime of t is equal to 2 minus 24e to the negative 0.025t all over t plus 4. So then what you want to do here is set that equal to 0. Now, a couple of things. This is not an easy equation to solve as an exponential function by itself. So looking at the top of this problem, it says a graphing calculator is required for problems on this part of the exam. What you want to know about the AP Calculus exam is that not only is the graphing calculator required in certain parts, you really have to use your graphing calculator in certain sections. It's just almost algebraically impossible to try to solve all of the types of equations they could throw at you in the time that you have allocated. So when you see this kind of problem, you want to either think that you're going to your solver or that you're going to graph and check where the graph intersects with 0. So go ahead and grab your graphing calculator, or if you just want to go to Desmos and plot the graph. I think because you'll have your graphing calculator and not Desmos on the AP exam, it's a good idea to get confident or to become confident on your graphing calculator to do this work. So if we plug this in, we have 2 minus, and then our expression is 24e to the negative 0.025, and then on your calculator that's going to be an x instead of a t. So if you plug that in, remember if you use your solver, you need to use the alpha solve button, and your calculator will technically be working like you'll have a guess, and then you need to evaluate the guess from there. So go ahead and get that put in. Just playing around with mine right here to get the equations all set up and ready to go. All right, so after I got that all input and checked it on my graph, the value that I got out for when this is going to be 0 is 6.261. So this is where I know that I'm going to have an extrema. But remember, there's going to be a little bit more work involved. I have endpoints here. So 0 and 24 are my endpoints, and I need to get out y values. So I've got 0, I've got 6.261, and I've got 24. So 0, I know the y output is 25. Then for 6.261 and 24, I need to take those x values, and I need to plug them in. But this is where we hit a little bit of a brick wall with our calculus tools that are available so far, because I want to plug those back into the original height equation. Right now I just have the derivative. So what I'm wanting to do here is take the derivative and work backwards. And that, more or less, is going to be all of second semester AP Calc. So what we can say here is that we're just going to plug this in. And then here, we're going to plug this guy in. Now we have to do that step because the second derivative test isn't going to tell us anything other than whether it's a maximum or a minimum. So when you have absolute and relative mins and maxes, you do have to go back to that original function to plug in. So we'd have to stop there. But that is an optimization problem, and that's kind of how you'll see them on the exam. Notice that that seems a little bit more like optimization that we did with graphical work than it's done with these applied scenarios where we have to do a big picture setup and we have to kind of come up with two equations. The optimization, I would say, tends to be a little bit easier than that on the exam, but it does really require that you work with the equations well and you work with your graphing calculator well. The last one, letter C, is also one of those ones where we have some of the information and then we're missing some of the information. But I think these are good problems to take a look at for the setup because it gives you insight into what are we able to do with calculus so far and where are we going to have to go in the future. So remember, anytime you're doing a tangent line approximation, you're just coming up with the equation for a tangent line, which is your y minus y1 equals your slope times x minus x1. So what we have here is y minus y1, and then the slope value is what we'd be solving for, the y1 value and the x1 value. So what we can do here is we've got an x1 value. That's your plug-in value of 16 here. So you'd have y minus y1 equals your slope times x minus 16. Then your m value comes from taking 16 and plugging it into your h prime of t. So we want h prime of 16. So if you just plug that straight into your calculator, let's see what we get out there. I get 1.196. So that's our m value. So we'll have y minus y1 equals 1.196 times x minus 16. So the one piece that we can't get here is the y1, because that's going to come from taking 16 and plugging it into h. So we need h of 16. And again, that means we have one step of working backwards that we don't quite have the tools yet to do, but we will within the next month or so. So what I want you to do is to hang on to this problem, because I think it's something that really does a good job of putting together all of the different pieces of things we've covered recently. You've got your related rates, you can do all of that. You've got optimization, you can do all of that with the derivative, except for the final piece of taking the value to plug back into your initial equation. And then your tangent line, we're almost good to go except for that last step of reversal there. So hang on to this last problem, because we will take a look at it again once we do have that process of, instead of function to derivative, we have derivative and go backwards to the function. So please let me know if you guys have any other questions from these problems. I know they're a little bit weirder than some of the ones we take home for homework, but I hope this gets you into a little bit more of an AP mindset for how questions might be posed, and also how you can deal with optimization in the real world. So you definitely won't have ones quite like this on our quiz. They'll be a little bit more on the predictable side of what we see on our homework and what we do in class. But again, email me if any other questions, and I hope you guys enjoy the rest of your Sunday.